Wonderful. So thank you very much, everyone, for coming to this One World seminar on the mathematics of machine learning. It's my great pleasure to welcome Tyrus Berry from George Mason University, who is going to talk about regression operators and extrapolation in machine learning. And thank you so much. The floor is yours. I'll say, if you've got questions, feel free to unmute yourselves or post them in the chat, and then I'll ask them for you. Thank you.
Thanks, Stefan. Yes, and thanks for inviting me. And feel free to jump in with questions as we go. Hopefully we won't get too diverted, but also I want to thank my collaborators, John Harlem and Dimitris Giannakis, and NSF for supporting a lot of this research. So we're going to be talking about sort of a lot of future directions and big questions that I have and ideas how I've been thinking about them. So I'll start with sort of the big monster hanging in the background, which is the curse of dimensionality. And basically the basic idea is that when you move into high dimensional spaces, the volume grows very quickly, grows exponentially in the dimension. So as dimension increases, the amount of volume that you have to fill up becomes quite large quite quickly. And so if we think about this in the context of like the standard regression problem where you're trying to learn some function, let's say it's a S times continuously differentiable function from a potentially high dimensional space Rn just to R, and somebody gives you n data points where they've told you the true values of the function or maybe slightly noisy values of the function. So you know the truth on some training data, then what you find in sort of a lot of different contexts is that the best possible error that you can obtain is inversely proportional to the amount of data that you have. So more data means smaller error, that's good. But the problem is it has this power here, and this power tends to have this 1 over dimension property to it, which really hurts the amount of, really hurts your control of error as the dimension gets large. And sort of one way to ameliorate that is to assume a lot of regularity. So S here, would be like the number of, you assume you'd have some bound on like the S derivative of your function. And, but more generally, this could be other types of regularity. And so what you find is you go through the literature and there's, all these various types of dimension and various types of measures of regularity. But one way or other, you always sort of end up in this kind of balance where, you can beat this curse of dimensionality by assuming more regularity, but it becomes a little bit unnatural. And so we start to look for other ways that we might beat the curse of dimensionality, or is there some way around this? I mean, this is sort of based on various different ways of trying to approximate this function using bases and things like that. And so is there at least in theory any way around this problem? So here are some of the standard ways that we might try to address it. So the first thing I call smooth it away. We just would basically assume you've got tons of regularity, right? But this is a bit artificial, right? Because so of course, if I assume S is proportional to N, then I no longer have this power going to 0 as dimension goes to infinity, right? But now I'm assuming sort of artificially that as the dimension gets higher, the regularity of the function I'm trying to learn gets higher for some unknown reason, right? And there's sort of no, at least a priori, there doesn't seem to be any reason to assume that. So, unless you could justify that for some reason. Now, maybe that you've got high regularity. And so I will be talking about sort of why this works. And it is actually a little bit delicate. How do you actually use the additional regularity if you know that it's there? So this is not completely trivial, right? But it doesn't really seem like a full solution to the problem. I should say all of these are sort of ways to kind of get around the curse of dimensionality. So the next way that you might get around the curse of dimensionality is assume that the function that you're trying to learn doesn't really depend on all the dimensions, right? So you say, okay, well, I've got this X, maybe it's really high dimensional. There's all kinds of complicated things going on in all the different coordinates. And they're not redundant or anything like that. There really is a lot of variability in my data. But the function that I'm trying to learn for some reason doesn't depend on all those. Maybe there's lots of sort of irrelevant variables or things that combine together to be important. So you should imagine that there's some function G that maps you to a much lower dimensional space, right? And that you could learn Y purely as a function of Z without having to know all the really high dimensional stuff, right? Of course, now you're left with the problem of trying to learn the G, right? But that's maybe something that you can address. So we'll talk about that. And then the one that I've been working on mainly in my research has been the redundancy assumption. And the interesting thing about this one is that it doesn't involve F, right? So these two assumptions, you assume either F that you're trying to learn is very smooth, or that the F doesn't depend on a lot of the variability. Here, this is not an assumption about F, this is an assumption about the data, where you assume that, okay, I collected all this data, right? But let's say that I was studying some phenomenon, right? So I didn't go off and just grab random bits of data from all over the place. I was selecting data that I knew was relevant to this one phenomenon, okay? And so one might hope that all the data that I've collected, you know, while it looks at various different aspects of that phenomenon, there's a lot of redundancies built in. So you could imagine that there might be, you know, even repeated variables or linear combinations of variables that are, you know, so that they're not linearly independent, or even nonlinear relationships between the variables. And so I'll show how that can, you know, basically this is going to imply that your data is going to live on or near some lower dimensional manifold. And then that leads to the idea of how can we use that lower dimensional intrinsic structure to alleviate the curse of dimensionality. So these are the three methods that I want to go through a little bit. So I'll start with talking about the smooth it away idea. And so the question is, why does assuming regularity or smoothness help me? And my answer is that basically what all sort of current machine learning methods do is they basically interpolate from either training data or some kind of landmark points that are sort of representative of the training data. So like if we go back to the very basics of a k-nearest neighbor regression or a local linear regression, right? What are you doing? You're going and you're looking at your, you know, k-nearest neighbors, and you're either averaging the function value of those neighbors, or you're, you know, doing some kind of linear regression. This is sort of like, you can imagine this A would be like the derivative of F. This is kind of like a next order, a Taylor approximation. And so this is what I want to focus on right here, right? So you're looking at X, this is some new input X that you want to know the value of your function at, and you're comparing it to Xj, your training data points, right? And you're sort of trying to interpolate linearly, in this case linearly, but later non-linearly. You're trying to interpolate from those training values what the value at the new data point should be. So, you know, the reason that regularity helps you here, right, is that the idea is you need to, you know, if you're going to be interpolating from nearby data points, you go to a high dimensional space, right? As the dimension increases, the volume of that space increases exponentially. And so you're going to need tons of data points to fill in that exponentially larger amount of volume, okay? How do you alleviate that problem? Well, if you assume F is very smooth, right? Now I don't need as many neighbors to be really close to me in order to do interpolation, right? If F changes very slowly, then I can interpolate far away from training data points validly. And so all I want to say is that all the other methods that are out there are sort of related to this, with maybe one arguable exception. So I work a lot on methods that are sort of evolved from kernel regressions, where we have some kernel function. This would be like some scalar shape function, which is typically like a bump function. And so the idea of kernel regression basically is you go and on all of your training data points, you put a little bump function, and then you use that as a basis, right? So you see what functions can I build by taking linear combinations of these bump functions. So these would be my bump functions. If you want to get a little bit fancy, you can put an ellipsoid, right? So you can have you know, have some major and minor axes. So this A matrix could be different around each data point. That's just getting a little bit fancy, but I wanted to make sort of a comparison here between this A and this A, right? And notice that they're multiplying the same quantity. And again, you're looking at the difference between your new input and the training data points. Neural networks are a little bit more subtle, but I'd like to make a sort of similar argument. So you look at your neural network, you typically have, again, some kind of activation function. Now, typically this would be a sigmoid, but actually in the old days, they would use like cosines, right? Which are actually kind of like bump functions, at least when you're near near zero. And so then you have this affine transformation, right? But I want to rewrite this affine transformation a little bit. So whatever the AJ here is, right? Whatever the weights are, I can always, you know, find an XJ tilde, right? Such that I could take the biases and write them as negative AJ transpose times XJ tilde, right? Because the bias is just one dimensional. This is like n dimensional. So there's always going to be actually lots of XJ tildes that satisfy this. And so then one could say, well, maybe take the XJ tilde that's closest to the data set among all the XJ tildes that satisfy this. And so if you do that, that allows you to rewrite this so that it looks at least superficially like the ones above. And so now I can reinterpret that again, assuming that H is like a bump function, I could again reinterpret this neural network as some kind of, you're looking here at AJ in some direction, right? And you're looking at, again, your new input minus, but now instead of one of your training inputs, you've got this XJ tilde, which is sort of like an artificial data point, right? It's like a synthetic data point. Now, the really cool thing about neural networks, I think, from my perspective, is that when we do these kernel regressions, we typically are constrained to using the actual data points as like we've sort of built our bump functions around our data points. But it actually makes a lot more sense to allow those points to move around, right? I shouldn't be constrained to using my my basis centered around my training data points. I should be able to move those landmark points around to find some better a better basis to represent that set of functions. So that's sort of my perspective on how you could reinterpret neural networks to sort of still be doing interpolation from nearby data points, but instead of the training data points, you sort of have these synthetic landmark data points that are being optimized. Now, of course, you wouldn't want to optimize that here because this would be massively redundant space in which to do the optimization. You'd want to do the optimization over here, of course, where everyone does it. But I still think it's a useful way to think about the neural networks as doing interpolation. So they still have this situation where sort of you need more neurons, right, in order to interpolate in a higher dimensional space. And then reservoir computers, if you're familiar with those, that's just sort of a special case of a neural network. All right, so why do I say these are all just interpolate? So just a quick demonstration of how these are sort of just interpolating from nearby data points. So here's a test case, right? So I've got a bunch of training data points that are all lying near the circle, right? Near the unit circle. And here's a function that I want to learn. The color here represents the function. It's just sine of 6 theta. So it's an oscillatory function. And so we have no idea what this function actually does away from the training data points. It's undefined, right? It could do anything. So here what I'm doing is I'm taking this function and I'm drawing it near, what I've done is I've taken the true function sine of 6 theta and I've multiplied it by something that decays exponentially away from the unit circle. So here I'm only sort of showing this function localized around the training data points. Okay, and so here if we do like a kernel regression, this is a diffusion maps, NYSTRÖM extension is kind of, it's really just reduces down to a kernel regression at the end of the day. So if you do a kernel regression or if you do a neural network, and I redid this also with a deep neural network, you get similar results, right? So all these methods, they do a great job of sort of learning the function given, you can see this is a fairly densely sampled training set. So if I give it enough data, I can learn a nice representation of my function near the training data set. But the cool thing is like, once you learn this function, right, it just takes any input from the plane and assigns it a value. So I can now see what are these functions doing away from the training data set. So now I'm going to not take away this multiplication by this function that localizes them near the training data set and zoom out a little bit. And so here's what they're doing away from the training data set. Now I say true function, that's a little bit tongue in cheek, right? Because who really knows what this function could be doing anything away from the training data set, who's to say? But if you wanted to take sort of just a constant, smoothest possible extrapolation beyond the training data set, then this is what you would probably do. And so that's sort of what the kernel regression does, right? The kernel regression just literally says, find me the nearest point in the data. Like when you get really far from the data set, it basically just says, find me the nearest point in the data set. Whatever it did, that's what I'm going to do, right? And so you see, you come out here and it just interpolates back to the nearest point on the data set. Neural networks are a little bit less predictable in what they do sort of near the far away from the training data set. Would you also consider SVM? That's a good question. So you mean like a support vector regression, I guess, instead of a support vector machine?
Yeah, if you only do regression, then yeah, support vector regression. Yeah.
Yeah, I mean, I think, the way that you train it is completely different, but I think, obviously like because you take it to this dual space to learn it, right? But then you can go back again, you can undualize, right? And I think you'll find that again, you have sort of these landmark data points, right? That it's interpolating from. But I haven't gone through, that's a good question. I should add that to my list and see if I can get it into the same interpretation. Good question. Yeah, so this is sort of the point is that like far away from the data set, you're either doing something kind of trivial and just finding the nearest point in the data set, or something's maybe unpredictable, right? In the case of a neural network. So, some people try to argue that you're sort of doing some kind of fancy extrapolation far away from the data set. And frankly, I'm not convinced. I'll show you some more evidence in just a second. Okay, so what about depth? What about the question of depth in neural networks? Well, so I just want to share sort of my point of view there real quick. So I think depth has to do with sort of multi-resolution analysis, right? So if we look at and what are multi-resolution analysis really good for? So if you use a basis like a Fourier basis, right, that's really good for representing smooth functions, right? Strongly regular functions like, S times continuously differentiable functions will be really well represented in a Fourier basis. You take a C infinity function and you add a single discontinuity or a single point of non-differentiability, suddenly that all breaks, right? You get really poor representation. You get Gibbs phenomenon and all this nonsense, right? But you go to a wavelet basis, right? A multi-scale resolution analysis, right? And you get, again, you can recover really nice, efficient representation of weakly regular functions. And now you just need like Sobolev regularity instead of strong regularity. So here basically, the idea is you've got these dilations happening, right? So this happens in a sparse grid. There's also sparse grids can also sort of get around the curse-of-dimensionality, but you have to make a regularity assumption, but it's a weak regularity assumption, not a strong regularity assumption. It's a Sobolev type regularity. And so the way that these works, right, are you have these dilations, right? So you've got a sequence of dilations and a sequence of translations. Now, sparse grids and wavelets, classical wavelets, they use nice grids. So their translations are just by actual like integer translations. And their dilations, right, they get to pick the dilations. They're just, typically these, 2 to the minus L dilations. So this was generalized to manifolds by Mauro Maggioni, actually. And he had a really, really clever idea, right? So first of all, his translations were based on the data points, right? So that's nice. So again, you're centering your bump functions on various different data points. And then you have to answer what's the right notion of a dilation. And so he said, well, what we have on a manifold is we have this diffusion operator, right? So the heat diffusion operator, and heat diffusion takes a function and kind of spreads it out like a dilation. And it sort of has a lot of the similar properties. So he used the heat diffusion to generalize dilation to manifolds. So similar idea there. So what does this have to do with depth? Well, okay, so I have to stretch a little bit here, but if you take sort of your standard deep neural network construction, right, where you use a piecewise linear activation function, right, like a ReLU or something, right, when you compose these multiple ReLUs with one another, what are you going to do? Well, you're either going to eventually hit by 0 at some point, or you're going to keep hitting by different A factors. Now, if you allow me to assume all the A's were just 2, right, then as you go deeper in the network, you're hitting by 2 to some power, right? So if you went K steps down in the network, you'd be getting hit by 2 to the K. And so you could envision this as sort of a multi-resolution analysis if, now, again, you're a lot more flexible here, right? Because rather than having to dilate by a factor of 2 each time, your neural network is allowed to optimize the dilation factors at each stage. And again, you've got these artificial sort of landmark shifts, translations that again are being optimized by the network. But so this could be one interpretation of why deep networks are able to do better than shallow networks, in that maybe we can show, and again, this is sort of just a speculative idea, but that maybe we can show that they require less regularity, weaker regularity than strong networks. So my attempt to try to, sort of unify all these ideas and come up with a sort of more general idea that sort of encompasses them all is, if we were going to build sort of an ultimate kind of framework that would work on manifolds or on our graphs or things like that, what would we want? So if we want to go to like sort of this weak regularity context, we would want something like a wavelet basis. And I think Mauro Maggioni basically got it right, that what you really need is you need some kind of diffusion operator, right, to generalize dilation. And I think he was on the right track with dilation, but what he's with translation, but what he's missing is the group element, right? So there's basically, you really want this nice correspondence between, Fourier transforms and convolutions. And so you need sort of a group of translations, right? You can't just, I mean, this works nicely to sort of center your bump functions and all the different data points, but you need an actual sort of group of translations. And so what you might look for is some kind of a frame of vector fields that could generate a group of translation elements. And then if you could build such a thing, you might be able to make some connection between convolution and the Fourier transform in that context. So again, this is quite a speculative idea, but I just want to sort of put together all these ideas. But at the same time, I want to point out that, again, this is all just based still on interpolation from nearby data points. We're just getting fancier. We're requiring less regularity, less sort of weaker regularity, but not really less. And so I just want to conclude sort of this this first part about getting around the curse of dimensionality by regularity to say that there does seem to be a solution. This was something that I learned by going back to Barron's result, Barron's paper on universal approximation this semester in teaching my course. There's this interesting theorem in there that essentially says that is like an existence result that says that there is a set of basis elements that get around the curse of dimensionality, but there's sort of some caveats, right? So what do you say? So you say, let's take a bounded subset of a Hilbert space. So these are going to be my basis functions, right? So if we were doing kernel regression, these would be a bunch of kernels based at some points y, right? So in kernel regression, you always take sort of bumps centered around various different points. And so these y's would not have to be data points anymore. They would be arbitrary points from my domain, right? The domain of the function that I'm trying to learn. So basically saying like you look at all your possible bump functions, okay, and y are going to be the centers, right, where those bump functions are centered, okay, which are now sort of landmark points, you might think, okay. Okay, so you got some bounded subset of a Hilbert space, and then you take any f that's in the closure. So these are all the closure of the convex hull of that set, okay, so these are all the functions that you could possibly learn. So f is just anything that you can learn. If it's in the closure of the convex hull, you have to play a little bit of a game here, right, where you put in the pluses and minuses of each of your basis functions so that you can get all linear combinations, because you have to take a convex hull. Okay, and so what Barron's said, so there's an existence result in the paper, and it has a really clever proof. So you should go back to Barron's 1993 paper to read this proof if you haven't seen it, because it's a really clever proof. It's very interesting how he proves it. But basically, so the idea is now any function that can be approximated, he proves that there exists for every n, there exists n basis functions. Now, for the kernel regression world, what that would mean would be there'd be n landmark points. So there's n special landmark points such that that function can be approximated by those n basis functions with an error that decreases like 1 over n, right? And there's no, so n here would be the number of basis functions that I'm using, right? And so there's no power here on n, right? Like 1 over dimension or anything like that, right? So there's no dimension dependence here. So this essentially says that there exists some bump functions, right? Now, that sort of get you around the curse of dimensionality. The problem is it's an existence result. First of all, it doesn't tell you how to find them. And then the other problem is that potentially as you change n, these functions would have to change completely, right? So it's not clear whether you could, if I go from n to 2n, can I use the same basis functions and like add on some new ones, right? Add on n more to sort of fill in the gaps, or do I have to completely change all my basis functions every time n changes? So there's a few things missing here, but it does at least suggest that there might be a solution. So there may actually still be hope to solve the curse of dimensionality, and maybe this is why neural networks are able to work, because they're again, they're not stuck using the training data points. They're implicitly moving the landmark points around, and maybe by doing a nice optimization, they're getting close to finding these n data points that achieve this smaller error. So that was news for me. I thought that was really fascinating, so I wanted to share it. But okay, so that's sort of the first thing, is that all these methods are doing sort of interpolation. And so I just want to sort of close this out by saying, like, what would extrapolation really look like, right? So that's interpolation, right? What's extrapolation really look like? So here's like sort of the example that I think of when I think of extrapolation, because this is something that none of those methods are really able to handle, right? So if you think about sort of a point, if I were to add a new point down here and say, what color should that be? Should that be red, green, or blue, right? The problem is all these methods, because they're based on interpolation, right? So if I add a point down here in the lower left corner, they're going to go to the nearest point from the training data set and say it should be green, right? Whereas we can all see that it should be red, right? Because we sort of continue the pattern of the spiral out. And so that would be extrapolation, would be if you could sort of look at a data set like this and learn that there's this pattern, right? And so how would you do that? Well, so first let me argue that none of these methods are doing it, right? So here's like sort of a kernel regression, and here's a neural network, and you can see they do sort of capture the spiralness when you're sort of zoomed in at this level of zoom. But if you zoom out and sort of ask them to extend the spiral further out, they don't really extend the spiral, right? So you come out here, right, and you see that all they're doing is sort of going back to the nearest point on the spiral, right? And so you can see it's sort of, you have that spiral pattern zoomed in the middle where it sees the training data, but when you zoom out, the spiral doesn't continue rotating like you would want if you were doing proper extrapolation. Let's see. So, okay, so I think the way that one could learn this in a systematic fashion, right, would be to try to learn a symmetry. Okay, and so what is about this that would allow me to learn it? So if you look at this data set, if I were to take this data set and shrink it down, right, if I were to sort of like just contract it towards zero, right, the reds would start to overlap with the greens unless I also rotated it, right? So if I were to take the red and shrink it by some factor, I would need to rotate it by some corresponding factor to get it to map back into itself, right? So the idea is that this data set actually does have a symmetry, right, which captures the spiral nature, which is that as you contract it, you need to also rotate it. And there's a sort of a ratio between the contraction and rotation in order to maintain the symmetry, in order to map the data set into itself. And so this is basically like one way that you could think about learning to do extrapolation is you look for a symmetry group that maps the data back into itself, or like mostly into itself. And if you could find such a group, then you could extrapolate, right, that other elements of the group might, should also map the data set into parts of it that you haven't seen yet, right? So then you think, okay, well, if this group element contraction and rotation gets me, and then the inverse of that, which is expansion and rotation in the other direction, should also map me into the group and so into the data set. And so that would then take these data points and move them further out and rotate them by the correct amount so that you would map red to red and green to green. So how might you try to go about finding these symmetries? If you're talking about learning from a manifold, one way that you can look for symmetries is by looking for repeated eigenvalues of your Laplacian. So the idea is that the Laplacian is, so a symmetry in a Riemannian sense would be a mapping from the manifold to itself that's an isometry. So that's a sort of maybe a rigid notion of what a symmetry is, but this is just a way to potentially get started. And so an isometry, because the Laplacian is just purely an element, purely a product of the geometry of the manifold. If you have any isometry of the manifold, that will preserve the Laplacian. And so that means it will map eigenfunctions to eigenfunctions. And so if you take an eigenfunction, if you have a symmetry of your manifold, then that means when you take any eigenfunction, you can apply that symmetry and it'll have to still be an eigenfunction with the same eigenvalue. Well, that means that your eigenspace has to be multiplicity greater than 1. And so basically it's a necessary but not sufficient condition to have repeated eigenvalues. And then the symmetry group is actually a subgroup of the orthogonal group acting on those eigenfunctions. Okay, so there is actually kind of a potentially way to find symmetries. The problem with this method is that it depends on having the whole manifold to begin with. So I'm not quite sure how to generalize this to the case where I only give you part of the manifold. So that's sort of an open question. But again, I'm just trying to think big ideas, like what would extrapolation really look like? And this is one way that I can think of what extrapolation would look like. It's looking for symmetries in your data set, or especially incomplete symmetries, and trying to complete them. I would think that those would be valid ways of doing extrapolation.
Can I ask? So a generic manifold may not have a whole lot of, say, isometries or good symmetries, but if you describe specific data, would you be thinking of something like a symmetric space or another type of non-generic manifold? Because a lot fully generic manifolds don't necessarily happen so often either.
Yeah. Well, so I mean, there could be special cases where you might think that you would have an actual symmetry, but more what I was thinking was, so you could imagine maybe you have kind of a lumpy torus that doesn't have an exact symmetry, right? But so you sort of do a little bit of a smoothing, right? And you could think about evolving the manifold, evolving your data set towards a highly symmetric data set. And as long as you've got the mapping between those two, right, then I can do my extrapolation over here and then map back to the less symmetric space, maybe. Again, yeah, I agree with you 100%, right? Symmetries are not generic, so we wouldn't expect to find exact symmetries. So we need some way to get around that. I really, if you think about it back here, what I'm really talking about is actually a symmetry of the ambient space. I'm really applying a sort of a dilation and rotation to the entire ambient space, not just to the manifold. So it could be that, one way forward would be to start looking for symmetries in the ambient space. But I think, it would be cooler to sort of find intrinsic symmetries. And I should say that there are actually, when I was starting to do some research into this area, there are actually a few, and I think it's mostly coming from sort of the physics constrained neural network world, people who are now starting to build neural networks that are designed to sort of look for symmetries, right? Because physicists sort of have this trick of, of looking for symmetries and finding new physics. And so, yeah, there are actually some new neural networks out there that they're trying to train neural networks that are specific. And so these, so I say that everyone's doing interpolation. That's becoming maybe less and less true every day as I think people start to find new ways to do extrapolation. I think this might be a really promising future direction. So it's something I'm very interested in.
Thank you.
Thanks. Okay, so moving beyond smoothing our problems away, right? What else can we do? So another method is the independence method, where the idea here is to assume that, yeah, I've got I've got a high dimensional data set. Yeah, it's got tons of different modes of variability. Yeah, they're all independent and doing different things. So they're intrinsically, it's high dimensional. There's no tricks that I can do. But the function that I'm trying to learn doesn't depend on most of that variation, right? The function that I learn depends on some lower dimensional projection of that high dimensional data set. And so the classic method here that I learned about, a few years ago. So again, these are things that, sort of didn't come across in my training until I sort of, fairly recently, actually. So the statisticians have looked into this, and they have something called like sufficient dimensionality reduction and a sufficient dimensionality reduction, and then there's some other name for it. But essentially the classical tool that they use is something called sliced inverse regression. And this is a linear method, and it's sort of like a supervised version of PCA. Okay, so in PCA, you look for a projection onto the sort of fundamental intrinsic space. But here you say, okay, there's lots of variability. Maybe the thing that I'm interested in might actually be in one of the very low variation modes, right? The function that I'm interested in, it may not depend on the principal components. It may depend on the principal components that have very small singular values, right? So like, why does the function that I'm interested in have to depend on the modes of highest variability? It might depend on modes of very low variability. And so what sliced inverse regression does is it looks for a projection such that the function that you're interested in is independent of the full data set given that projection. So if you tell me this projection, I don't need to know anything else from the data set in order to represent the function that I'm interested in. Now, so this is not, obviously it's not always true that such a projection exists, but they do have some conditions under which, so if there's some conditions under which you can show that such a projection exists. And so then the idea would be you can use sliced inverse regression to learn the beta, the projection, which is sort of like the PCA projection, except that you're learning the thing most relevant to your desired function rather than just the thing of highest variance. And then once you learn that projection, now you're down to a lower dimensional space, and now you can do a regression again without worrying about the curse-of-dimensionality, because hopefully this M dimension is much lower than the ambient, original dimension of your data set. So the picture I like to show for this is, imagine somebody gives you this live feed from Times Square, and you're asked to figure out if somebody's in the crosswalk or not, right? So you're come up with a machine learning algorithm to figure out if somebody's in the crosswalk, right? Well, there's huge amounts of totally independent variability in here. There's all these billboards that are going to be flashing up all this information, right? There's a huge amount of information in this. I can't say that this is low dimensional in any sense of the word, right? But actually, most of this variability has nothing to do with my question, right? Like, what's going on in this billboard is not going to tell me anything about whether somebody's in the crosswalk or not. So I could essentially cut off the whole top half of this image, right, and reduce my dimensionality enormously. And that would not help, that would not hurt my ability to predict the function that I'm interested in. Okay, so more generally, you would need to learn a nonlinear projection. So rather than just beta transpose times x, you would need some beta function that projects you down a nonlinear projection to a lower dimensional space. And that's rather difficult. There are sort of kernelized versions of this, but I'm a little bit skeptical of those because the whole idea of a kernelized version is that it sort of uses neighbor relationships to do an interpolation again. Right, and you can't use neighbor relationships to do interpolation in this high dimensional space because it's truly intrinsically high dimensional, and so that means that it's going to be very hard to find neighbors that are representative of the target function of interest. So I haven't worked with these kernelized versions too much, but I'm a little bit skeptical of them. I should say that I have worked with the slice inverse regression, and it is quite powerful as a linear projection. Okay, so that's independence. I haven't done too much on it, but I do think that's an important consideration when trying to get around the curse of dimensionality. If you can get rid of dimensions, that's all to the good. Okay, so then the last direction, this is the direction that I work on mostly, and it has to do with redundancy. And so here again, like I said before, the function is not involved. This is a question about your data set, right? So it's not about what function you're trying to learn. It's just a question about the modes of variability in your data. And so here, typically the hope is, this is sort of more effective typically on kind of scientific problems where the data collection is not sort of quite so haphazard, and you're really taking in a bunch of correlated data that's all relevant to what you're interested in. So you can imagine, right, obviously if I had like some coordinate in my data set was always 0, right, I could just get rid of that. That's obviously irrelevant, or it was just constant. It's not informative. By the same token, if one of my coordinates was just always a linear combination of the other coordinates, right, and every single data point, this nth coordinate is some linear combination of the previous ones, that's a redundancy. I can get rid of that variable. It's not gonna help me at all in trying to learn the function. The information is already contained in the remaining data points. So more generally, if you had a bunch of linear combinations, right, you represent this as some matrix that maps your data set, maps each one of your data points to 0. And that's what PCA does, right? So PCA finds the orthogonal projection that gets rid of all those redundancies. And of course, we have to soften this a little bit, and we don't talk about exact redundancies, but if we lie very near a hyperplane, right, we're sort of on a fuzzy hyperplane, then we have some small singular values. We can get, those are approximate redundancies. Okay, and so the cool thing about this is that if you can project down and reduce the dimension, right, of your data set without really eliminating any information, then that will help you learn any function, right? So that's always valuable. And so what does this have to do with manifolds? So the idea is if we generalize this to say that rather than a linear redundancy, we have a nonlinear redundancy. So some nonlinear functions that are always equal to 0. And so now the idea is, so let's say I've got n minus m redundancies, right? So conveniently, right? Somebody gave me some n-dimensional data, but there were n minus m redundancies, right? So of course that means that the residual dimension is going to be m, right? Because I've got n minus m sort of redundant dimensions. Okay, and so if this is the case, right, and if the H is sufficiently smooth, right, then Sard's theorem tells us that almost every value in the domain is regular. So that means either 0 is regular or regular values are dense. So there's going to be regular values arbitrarily close to 0 if it's not a regular value. And the regular value theorem tells us that the inverse image of a regular value will be a manifold of dimension m. And so that's sort of the connection to manifolds, right? Why should we think that there are manifolds in our data? Well, maybe there aren't in general data sets, but if we believe that there are nonlinear redundancies, right? If we believe that our data set is correlated, that the coordinates of our data point are related in some potentially nonlinear ways, then that means that there's actually a lower dimensional manifold living inside of our data set. And of course, we may not, generically, we wouldn't expect our data set to live exactly on a manifold because we wouldn't expect these redundancies to hold exactly. But we might expect our data set to be near a manifold because these redundancies might be approximate, right? Rather than being equal to 0, they might be equal to some small noise. Okay, and so now the question is, so now we know that sort of sort of generically, under smooth enough redundancies, we should expect our data set to live near a lower dimensional manifold. So then the question is, how do we leverage that structure? And so, of course, you could go off and try to learn the manifold, right? You could try to build a, some kind of simplicial complex that approximates the manifold. That would be one way of trying to learn the manifold, but it's not clear what you would do once you had that simplicial complex. And so we know that in this context of redundancies, we know that there's a manifold out there. And the question is, like, what do we do with that knowledge, right? Knowing that there's some manifold, we don't know what the manifold is. We just know that it exists, right? Because we're not assuming that we know what the H is, right? I'm not assuming someone told me what the redundancies are. I'm just assuming that there are these redundancies that I should be able to take advantage of somehow. And so knowing that there's a manifold, I claim that what we're really after is not the manifold itself, but we're really after a nice basis for the space of functions on the manifold, right? Because it gets, at least in this context where we're trying to do regression, it's fairly obvious that what we want is a nice basis to represent functions on the manifold. And moreover, we'd like them to be adapted to the intrinsic regularity with respect to the manifold. So we don't really care about regularity with respect to the ambient space, because in fact, we expect the functions to be not very regular, right? Because if the function really lives on a manifold, then that means I really have no control over what's happening off the manifold, right? And like, I don't really know what's happening off the manifold. So I really want to, if you think about, the function might actually change really rapidly, sort of if you move orthogonal to the manifold. So I wouldn't expect it to sort of be regular in the ambient space, but I do expect it to be regular intrinsically as I move along the manifold. So this is where the idea of manifold learning as learning the Laplace-Beltrami operator comes in, because the Laplace-Beltrami operator gives us a way, it's basically its eigenfunctions are always a basis for L2 space of the manifold, but moreover, the eigenfunctions minimize this Dirichlet energy, and this Dirichlet energy measures sort of how rough your function is, right? Because it's sort of integrating the norm of the gradient of the function. So if your function is sort of highly oscillatory, right, then it's going to have a really high energy. And so the first eigenfunction of the Laplacian is always just the constant function, because that's the smoothest possible function. And then the next eigenfunction provably has a single oscillation. So it has sort of this zero set, and it's positive and negative on either half. So it actually cuts the manifold into two pieces. And so what's really happening here, and in fact, like on a circle or on a real line, these eigenfunctions are exactly the classical Fourier bases, right? The classical Fourier functions. And so what's really happening here is I've built the eigenfunctions of the Laplacian are giving us a custom Fourier basis that's adapted to our manifold. And in fact, if you're on a graph, you're using the graph Laplacian, then you're sort of getting a discrete graph Fourier basis. That's kind of a common thing that's going on in graph theory also. So when I say like we want to learn the manifold, if we're really after trying to get a nice basis for functions on the manifold, then learning the manifold is really about learning this Laplace-Beltrami operator, because and learning its eigenfunctions, because that's going to give us this nice basis. And so that's where this perspective of like how do we learn a manifold? It's a bit weird, right? We don't actually care like what the point set of the manifold is. What we really care about are these basis functions, and so that's why we want to learn the Laplacian. And so this is where Laplacian eigenmaps and diffusion maps come in, because Laplacian eigenmaps and diffusion maps showed that when you build a certain kind of graph Laplacian, so you take your data set, you build like a k-nearest neighbor graph, and you build a certain kind of weighted graph Laplacian. And if you normalize it correctly, you can prove that that weighted graph Laplacian will actually converge to a Laplace-Beltrami operator on the manifold, assuming that the data came from a manifold, right? But we believe that the data comes from some manifold if we believe that there's these redundancies. And so what that allows you to do is that, that's going to give you these basis functions that will allow you to do interpolation in a way that enforces intrinsic regularity rather than extrinsic regularity. So the way that the diffusion maps algorithm works is you're given some data points that you assume. So you assume they lie exactly on a manifold inside of a Euclidean space, but there's some robustness results, although I should say that more work needs to be done on sort of robustness to noise, but there are at least some basic results that say that these the eigenvectors and eigenfunctions that you get are robust to adding some noise off the manifold. So given these data points that lie in the manifold, you build what we call a kernel matrix. The kernel matrix is sort of just a data by data matrix. So if you've got n data points, it's n by n. And you get that by applying this shape function, some kind of shape function. It doesn't have to be exponential, but that's the most common. It has to decay, essentially it has to be a localizing function. So that points that are far away get very small values in the kernel, and points that are very close get larger values. So these are going to be the weights of our graph. This kernel matrix gives us the weights of our graph, and then we build a degree matrix by summing up the rows of our graph of our adjacent, or sort of our weighted adjacency matrix. And so now we're going to build a graph Laplacian, but just with this tiny twist that we do this normalization first. So typically when you build a graph Laplacian, you would do this sort of Markov normalization to turn your kernel matrix into a Markov matrix. And then you would do identity minus the Markov matrix to get the generator of that Markov process, and that would be your Laplacian. And what they found is that essentially that works as long as you assume that the data is sampled uniformly, meaning sampled according to the volume measure of the manifold. But the volume measure is sort of inherited from the ambient space, right? From the embedding into the ambient space, there's an implied geometry, the inherited geometry from the embedding, and that has a certain volume form. And there's no reason to assume that you've sampled according to that volume form. So like if you have a unit circle, there's no reason to assume that the points are sort of nicely uniformly spaced. They could be sort of bunched up more on the right side and more sparse on the left side. And so in order to sort of debias and compensate for that potential sampling, that's where this other normalization came in, which I call right normalization, which essentially debiases by, so the idea is that this first D that you estimate here, this degree matrix, is essentially a kernel density estimator. And so by pre-dividing by that density estimator, you debias your kernel, and you can prove then, if you do that, then you get a graph Laplacian matrix. And so it's just a graph Laplacian on your data set, but you can so now the idea is this matrix is like an operator, right? And so if I think of, it's an n by n matrix. And so if I think of a vector, an n by 1 vector, that's sort of like a discrete function, right? So it's assigning a value to each data point. And so if I take my operator, my discrete operator, and apply it to my vector, then, sorry, there should be an F here. So that's equivalent to applying the Laplace-Beltrami operator to the function F that was discretized, plus some errors that depend on the bandwidth and the number of data points. And here we get a curse-of-dimensionality. So notice that, so this basically, there's two terms here. There's a bias and a variance term, essentially. And in order to make the bias small, you need to make the bandwidth of your kernel small. But as you make your bandwidth smaller and smaller, your variance blows up because delta is in the denominator here. And it blows up with a power that depends on D, which is the intrinsic dimension of the manifold, okay, which we don't necessarily know. We could estimate it, but what's really interesting is you don't actually need to know it for this algorithm. You don't need to ever estimate the dimension. But the intrinsic dimension does control the bias variance trade-off. And so if you sort of optimize the bandwidth with respect to the number of data points, you get a cursive dimensionality that's intrinsic rather than extrinsic. So estimating this Laplacian has an error that depends on the dimension of the manifold, but it's independent of the dimension of the ambient space. So it doesn't matter how big the ambient space dimension is. All that matters is the dimension of the manifold. Okay, so it's running short on time. So the idea here is that this gives you a custom Fourier basis, right? So here's an example on a data set that was so that I use the algorithm here. So this is a data set sampled on the cap of a sphere that I sort of cut out with a funny boundary, and you get your sort of constant function, and then this would be like sine, and this would be like cosine, right? You got two phases there. This would be like sine of 2 theta, right? And then you get higher and higher, more oscillatory functions. But then because this is a manifold that has interesting geometry, you get things that aren't just sines and cosines. You get interesting things, interesting Fourier functions that respect the geometry of the manifold. So that's the idea here, is you get this cool custom Fourier basis. And so then now what can you do with this? Well, of course, you can use this to do interpolation, right? This is a basis. So I can try to represent my function, given some training data points where I tell you a noisy value of the function or the true value of the function on the training data points. I could now represent that function by projecting it and essentially doing like a low pass filter in this Fourier basis. So you can use this to do regression, and that's nice because it does it enforces an intrinsic regularity on the function. So it forces it to be a smooth function of the manifold. And it doesn't try to make it regular in the ambient space. It tries to make it regular as a function of the manifold. So that's nice, but that's, again, this talk is called Going Beyond Regression. So let's go beyond regression here. So what might you do that's a little bit more ambitious than that? So let's say that you have a map between two manifolds that are potentially arbitrary manifolds. So these are living in ambient spaces, right? So I've got some data set over here and it's mapping over to some other data set over here. And so I could try to learn the mapping between those two, right? That's one thing, right? But maybe what I want to do is something a little bit more ambitious than that, which is that when somebody comes in with a new input, they're not going to tell me it's this, right? What they're going to tell me instead is here's some probability distribution about where the input might be. And I want you to map that over to the output space to figure out what's the probability distribution on the output space, right? So not just a straight input-output, but now uncertainty quantification as well, right? Okay, and so the idea now is that the manifolds don't need to be the same dimension. They don't need to be, similar in any way, right? This can be some arbitrary map that could be many to one, or it could actually even be one to many. It could be a stochastic map. So now the idea is what's really going on here is I've got an operator that takes density functions on the M manifold and maps it over to density functions on the output manifold. And it turns out that that's a linear operator, in fact. So there's a linear operator that takes density functions on M and maps them over, right? Because there's this mapping between M and N, implicitly a density function in M will get pushed over through this operator onto a density function on N. And so if this is just a linear operator, then I can represent it in this basis. So all I have to do now is use diffusion maps to build a nice Fourier basis on M, use diffusion maps to build a nice Fourier basis on my output space, right? And now all I have to do is estimate this mapping that takes me from basically the matrix representation of the operator in those bases. And conveniently, a little bit of calculus will show that the way that you estimate this, the entries of this matrix are you take eigenfunctions and you compose them with the function. Now, all that means is you take the eigenfunction over here and you just push it onto the output space, and then you take its correlation with the output eigenfunctions, the eigenfunctions on the output space. So then once you give me if you give me an input probability distribution that you want to push forward, all I'd have to do is take its Fourier transform to get its coefficients in the Fourier basis, multiply it by the matrix representation of the linear operator, and then do an inverse Fourier transform on the output space to get a representation of the output. So let me just show an example of this. So here's like an input space that would be an annulus, and let's say I map it down to the circle by just collapsing the radii. Okay. So I've got an input manifold, output manifold. I can learn a basis on each of them. Now I'm going to draw both of their, because every point here corresponds to a point over here, right? I'm going to actually draw all their bases on the annulus. Okay, so I did diffusion maps on the annulus, and these are the bases that I got. Notice some of them are angular dependent and some of them are radially dependent. And then I did diffusion maps on the circle. Okay, but I drew their eigenfunctions on the annulus just so you could see that they're all purely angular dependent, right? Because there's no radial variable here anymore. Okay, and so then I've got a mapping that takes me from each point here, maps over to the circle. And so I then learned the matrix representation of that mapping, right? Which is basically just a correlation matrix between the eigenfunctions here and the eigenfunctions here. And so this is the correlation matrix that you get. This is the matrix representation of the operator that maps densities from the annulus to the circle. And so then you could take a density on the annulus and you could map it down onto the circle, and see what it does is it sort of makes it radially independent, right? It sort of averages over each radial line to get your new density. And in this case, this was a simple enough problem that I could actually analytically compute what the true output should be for this particular input, and compare it to this process. And then you can do more complicated examples. So here's an input. So again, I'm drawing these all on the annulus, but this is really, because this is purely angular, it has no radial dependence, right? This is actually a density on the circle that I'm just drawing on the annulus for clarity, because otherwise you wouldn't really be able to see it. But so if you take this probability distribution and map it onto the circle, notice that because there's a lot of right? Even though this is densest in the middle here, right? Because, when you map it to the circle, you have to integrate over this whole line, and there's a lot of volume here that's getting collapsed down, right? The output is actually has peaks is actually bimodal, right? Even though the input is unimodal. So again, this is all done with this idea of just using the matrix representation of the operator. So any linear map between data sets you can use. And so another way that you can do this is for forecasting, right? So forecasting is just a map from a data set at a certain time to a data set in the future time. And so here, all we have to do is to compute the matrix representation of that map. It's just the eigenfunctions at the current time correlated with the eigenfunctions at the future time. And you get a matrix. So this is for the Lorentz system. You get a matrix representation of the Lorentz dynamics in this basis. You can use that to do forecasting. You can predict the average, you can predict the variance of the output. You can even, we use this for El Nino, and this is a different example, but for El Nino, you can, because you're predicting a probability distribution, the El Nino event is technically defined as like the El Nino index going over 0.5. And so you can actually predict what's the probability of an El Nino event at some time in the future. And then, so here's an example of doing this on the Lorentz 96 or the Lorentz 63 dynamics. So here's a probability distribution and a training data set. And I'm going to push this forward using this method. And at the same time, I'm going to take an ensemble sampled from the same distribution and push it forward using the true dynamics. So if I push that forward a little bit, you can see, right? You can really push forward the whole distribution forward in time. And so now you're not just making a prediction about like what's the mean, right? Because I had an uncertain input to begin with, and so when I get my prediction for the future, I could ask like, what's the probability that it's on the left half of the attractor, right, at some time in the future? And again, it's not perfect, but it's actually maintaining a lot of coherent structure with what's going on in the ensemble forecast. So this is some of the things that you can do to go beyond regression, and maybe I'll stop there. These are some of the references that I was talking about earlier, with various forms of the curse of dimensionality that I've run into. Maybe I'll leave that up. Thank you.